Hello, and welcome to this technical presentation released to support our research for the 11th Annual IEEE Information Technology, Electronics and Mobile Communication Conference, held virtually and hosted in Vancouver. I'm Jamie Blanche, and I am a research associate working for the Offshore Robotics for Certification of Assets Hub at Heriot-Watt University in Edinburgh in Scotland. Working in partnership with the Smart Systems Group and Microsense Technologies Limited, we are located at Heriot-Watt University's Riccarton campus. I am pleased to introduce our research, Asset Integrity Monitoring of Wind Turbine Blades with Non-Destructive Radar Sensing. I'll open this presentation with a brief overview of what's to come. I'll start with the technical challenge, where the need for non-contact defect detection in wind turbine blades is defined, followed by an introduction to the millimeter-wave sensing method used and the advantages of this method. Then, I'll outline the motivation and value creation of millimeter-wave sensing. I'll frame the problem of wind turbine operationally induced defects and common failure modes before introducing our test blade specimen. Then, I'll walk you through our required laboratory results before providing you with an overall wind turbine integrity inspection summary. This will be followed by a technical summary and rounded off with a brief on our parallel and future works with the millimeter-wave sensor. Finally, our publications list is available along with our author biographies and project contact details. To provide an overview of the technical challenge for offshore renewable defect detection, reducing operation and maintenance downtime results in greater asset productivity. Shutting down an asset for inspection is costly, and operators tend to do so only when an asset has an externally observable defect, which is sometimes too late to mitigate at an early stage. This results in costly and time-consuming repairs. By contrast, non-contact internal structural sensing, deployed by drone for example, offers earlier warning of defect onset at a fraction of the operational cost normally associated with asset inspection and defect detection. The key challenges in the offshore environment are centered around how to optimize inspection scheduling in the harsh and higher maintenance environment of offshore renewable energy generation farms. As new manufacturing technologies make wind turbine assets ever larger, wind farm sites tend to be situated further and further offshore. Accessing these tall structures, often 100 meters or more, becomes a practical and logistically complex problem in a wind farm environment situated some 100 kilometers from shore. Consequently, there exists a need for quicker, holistic measurement techniques that are easy to deploy and operate remotely. To outline our method, we have employed the novel application of frequency-modulated continuous wave radar in the K-band for analysis of porous composite structures. We have approached this problem using patented microwave sensing methods which have been applied to several use cases. And although we are focused on wind turbine blade integrity here, our publications list and YouTube address shown at the end of this presentation showcase our parallel millimeter wave sensing applications. The common thread from all our research using this sensor has shown that the key advantages of FMCW show it has a lower power output with low demand on power systems, is a non-contact and non-invasive sensor with an appreciable range, has proven high sensitivity to water, oil, and porosity, and has real runtime front-end data analysis capability and is suitable for low latency data telemetry with a roughly 30 millisecond computation time. Having addressed the technical challenge, the key motivation of millimeter wave sensing is to reduce risk to both personnel and operators by offering an alternative to human inspection teams and the requirement to access hard-to-reach areas in hazardous or difficult environments. The system offers the ability to monitor key wind turbine blade structures from a safe distance while providing data via live telemetry for augmented reality applications and for integration with centralized digital twin architectures, thus offering an alternative to rope access teams, reducing risk to life and the asset in a challenging offshore environment. Our motivation has also been to reduce costs. Providing new, previously inaccessible data, this represents an enhancement of asset and environmental understanding via the provision of real-time data for further analytics and integration with synthetic environments. Importantly, for offshore and hazardous environment roles, this unique non-contact method provides an internal measurement of defect onset or contrast versus the measured baseline in asset condition, allowing for early detection of critical defects, specifically delamination and water ingress. Delamination and water ingress are inherently internal defects that are not often visible from the asset exterior. Defects and common failure modes. Wind turbine blades are subject to differing operational loads and defect types. The most common are derived from flexing of the structure during operation and weather abrasion. These are manifested in cracks, delamination, resulting in saltwater ingress via spray in offshore conditions, structural deformation, and material loss at leading edges. Specific defect types are grouped into 7 distinct categories. For this demonstration, we have focused on Type 4 defects to test for internal damage modes not usually visible from the asset exterior. Presenting the test specimen, our test section of wind turbine blade is predominantly a sandwich composite structure of balsa, polymer, and fiberglass laminated layers. Some metal components, typically lightning conductor cables and tensioners, are also present. This structure is typical for most small to medium wind turbine types. Our sample is 1.5 meters long, 90 centimeters high, and 40 centimeters at the airfoil chord where the polymer main spar can be seen. To give an insight into the experimental setup, you can see the radar antenna to the right of the damaged wind turbine blade section in the picture on the right. For these experiments, the antenna to target distance was a constant 10 centimeters, irrespective of the area under investigation. However, the distance for measurement can be many meters, depending on the desired field of view. I would ask you at this point to take note that the Type 4 delamination defect is situated on the inside edge of the wind turbine laminated structure, an internal defect, and is not directly visible to an observer outside. A camera on a drone or a rope access team, for example, would not be able to see this defect. The key results from this laboratory work can be observed in figures 1 and 2. Figure 1 on the left is a comparison of return signal amplitudes in the frequency domain for a healthy section of wind turbine blade wooden core structure versus a section of the wooden core structure exhibiting a Type 4 defect. In frequency domain datasets, the x-axis can be considered a distance measurement from the sample, with an interfacial peak observed at bin 5, which corresponds to the target distance of 10 centimeters from the antenna. If the target is further from the antenna, the interfacial peak will occur at a higher bin number. For the undamaged area of the tested blade, the peak is represented as a solid blue line with the higher amplitude, which can be taken as a baseline and represents the porous, low dielectric structure of the balsa glass epoxy polymer. The red dashed line represents the Type 4 delaminated area shown in the previous slide, has a consistently lower return signal amplitude both at the interfacial peak at bin 5 and the residual signal decay of the delayed returns due to the porous nature of the material. This consistently lower amplitude represents the added porosity of the observed delamination in the sensor field of view. Figure 2 on the right is the dynamic return signal amplitude of water deposited into the same area of internal delamination shown in Figure 1 and the previous slide. The x-axis in this case is time, with the 3 milliliters added at 3 minutes and 40 seconds into the experiment duration. Clear signal contrast for even this trace volume of water can be seen from the sensor's output data. Remember, from the previous slide, this defect is located on the inside edge of the wind turbine structure and cannot be visibly observed from the blade exterior. To summarize this wind turbine integrity experiment, we have demonstrated the increase in demand for non-destructive testing to evaluate the state of a wind turbine blade. In removing the need for personnel to operate in harsh environments far offshore, the deployed FMCW, be it autonomous robotic platform or embedded within the structure, provides asset inspection solutions that save time and expenditure by detecting defects earlier. We have demonstrated the effectiveness of the sensor for surface and subsurface faults within the composite. Clear and distinct contrasts in return signal amplitude have been observed for an area which is classed as healthy versus an unhealthy delaminated section of wind turbine blade. We have also observed the clear contrast in return signal from 3 milliliters of water ingress when applied to that same delamination defect. The millimeter-wave sensor system represents an innovative non-destructive evaluation technology. It requires no optical or visual contact with the asset and can relay vital information on asset integrity in scenarios where optical systems fail. The sensor is deployable, having been ruggedized for real-world deployment with results relayed to digital twin and augmented reality systems in runtime, currently at technology readiness level 6. The sensor can see property changes in a material that is both covered and obscured by non-metallic coatings. It is capable of distinguishing target types and human presence within highly restricted and often harsh operating environments. The boxed image on the right shows the sensor during flight tests on a small quadcopter drone system. Further integration of this platform-agnostic sensor suite with trusted autonomous systems will allow not only improvements in asset management efficiency by providing runtime data integration with the synthetic environment, but will also help systems to conform to safety compliance requirements imposed while working in the offshore environment, while providing holistic infrastructural state of health data to nearby autonomous and human operators. Ultimately, millimeter-wave sensing represents a low-power, low-cost payload that could not only navigate terrain and obstacles, but also form the basis of a lab-on-the-bot for materials analysis applications in harsh environments, providing asset integrity, target identification, and environmental data for live telemetry to a digital twin system for human-in-the-loop and parallel autonomous systems to utilize. Further work to improve current experiments for material and defect type characterization will include improved graphical user interfaces for data representation. This will include two-dimensional area mapping, three-dimensional depth mapping, and four-dimensional dynamic depth defect mapping. We are also exploring multispectral sensing in the microwave and terahertz bands, where the variation in inspection frequency will inform higher resolution defect types and new measurands. We have achieved multiple successful deployment cases using this sensor in parallel projects to detect corrosion on metal surfaces, salt on roadways, and metal and fluid presence within sandstone and concrete structures. These have been achieved during both full integration with an autonomous ClearPath Husky wheeled robotic platform and via integration with human-operated systems, such as handheld devices or integrated with human-operated service vehicle systems. Further integration of the platform-agnostic FMCW sensor suite with trusted autonomous systems will allow improvements in asset management efficiency, saving costs in OPEX and CAPEX while preserving the longevity of the renewable energy asset. While you are at this conference, I invite you to view a presentation by my co-researcher and colleague, Mr. Daniel Mitchell, which is titled An Evaluation of Millimeter-Wave Radar Sensing for Civil Infrastructure. Daniel's work represents another parallel use case of the millimeter-wave sensor and is applied to the internal inspection and subsequent maintenance scheduling of the large and complex concrete infrastructures which provide essential services such as energy, transport, water, and waste management. This is achieved by the non-contact, non-invasive detection of corrosion and corrosion precursors within steel-reinforced concrete structures. If internal asset integrity inspection is of interest to you, Daniel's research is well worth your consideration. We invite you to view our other published research outputs. Thank you for watching this presentation on the unique application of millimeter-wave sensing for wind turbine asset integrity. We at the Offshore Robotics for Certification of Assets Hub, the Smart Systems Group, and Microsense Technologies Limited look forward to future engagements. You can also visit our YouTube channel, Smart Systems Group, or Orca Hub websites to view our latest research presentations, public outreach, and news features. Simply type Smart Systems Group Heriot-Watt University or Orca Hub into the YouTube search bar or follow the web addresses provided. If you have any questions regarding any of the work presented here or any of our previously published works, you are most welcome to reach out via email or via our project websites and associated social media platforms. Brief project author biographies and company contact details will follow this slide.